Suppose you're in a machine learning engineering interview and the interviewer asks you this: why don't we just use a simple byte-based tokenizer? It has a fixed 256 token vocabulary, it's simple, and it never has an unknown token. Why are we still using a complex BPE tokenizer? Pause the video and think about how you would answer. When you're ready, press play, and we will test your first move. The answer almost everyone reaches for is that BPE groups characters into subwords, and that subwords carry more meaning than bytes. Here's the sentence we are keeping for the rest of the video. Summarize the attached quarterly report in 3 bullet points, which is 63 bytes of ordinary English, and here is how GPT-4o's tokenizer splits its first word. It cut the word into some, then are, then eyes, and if this were about meaning, it would have cut between summer and eyes, where the word genuinely divides. It cut where it did because at that point in training that pair was the most frequent pair left in the corpus, and frequency is the only criteria BPE has. You can see that in the vocabulary itself. These are 40 entries sitting next to each other, and most of them are not words or even parts of words. That leaves the question's other claim, which is that a byte tokenizer never produces an unknown token, and that this is a reason to prefer one. So let us take the tokenizers for GPT-2, GPT-4, and GPT-4o, and count how many of the 256 possible byte values appear in each vocabulary as tokens in their own right. All 256 in all 3 tokenizers, and that happens by construction, because Byte-Level BPE starts from the 256 bytes and adds merged pairs on top, which is why GPT-2's 50,257 entries are 256 bytes plus 50,000 merges plus 1 special token. So the byte tokenizer is not the alternative to BPE, it is the bottom 256 rows of BPE's own vocabulary, which means there is no choice between 2 designs here. There is one axis and a question about where on it to sit. What those rows by is length and only length. Our sentence is 63 bytes, and through the same tokenizer it is 12 tokens, and running that comparison across a whole book of 738,000 bytes of English prose settles at 4.33 bytes per token. Byte-5's authors measured 4.1 on a different corpus with a different tokenizer. So feeding that text as bytes costs roughly 4 times as many positions as feeding it as BPE tokens, and that number is billed 4 separate times. Go byte level and you pay 4 times the positions through every layer in training, and 4 times as many sequential steps to write the reply, because generation emits 1 position at a time and cannot be parallelized. You pay 4 times the KV cache for the same conversation, which cuts how many users fit on a machine, and the same context window holds 4 times less text. 4 times longer sequences, 16 times the compute, because attention is quadratic. That is the answer, or so you may think. But that is not fully correct. A transformer does 2 kinds of work on every position. The weight matrices do the same work per position, however long the sequence is. Attention does not, because each position compares itself against every other one, so that work grows with the sequence. So making the sequence 4.33 times longer makes the weight matrix work 4.33 times bigger, and the attention work 4.33 squared times bigger, which is 18.8. That squaring is where 16 comes from, and 16 is not wrong about the squaring, it is wrong about how much of the model is doing it. How much is doing it depends on the sequence length against 12 times the model width, a ratio from Kaplan and colleagues. At Llama 3.8b's width of 4096, a 2000 token document puts about 4% of the work in attention. So 96% of the bill grows by 4.33 and 4% grows by 18.8, which adds up to about 4.9. The quadratic term does exactly what everyone says it does, and it still only moves the answer from 4.33 to 4.9. That 4% is set by sequence length, so it grows. An 8,000 token document costs about 6.4 times, and a 32,000 token document costs about 10 times, because attention is 14 and then 40% of the work. The 2 kinds of work are equal only at 49,000 positions. 16 is where this curve is heading, not where most documents live. Byte-5 is a byte-level model trained alongside MT5, its subword twin, and its authors report that across all model sizes it requires about 1.2 times more operations. If 1.2 is the real number, everything we have just derived is wrong. It is the real number. So the question to ask is, what was held fixed when it was measured? Both models were pre-trained at a sequence length of 1024, which for MT5 means 1024 subword tokens, and for Byte-5 means 1024 bytes. So at every training step, Byte-5 read roughly 4 times less text. Byte-5 did not avoid the cost of longer sequences. It paid that cost by seeing less text, which an operations count does not show, and 1.2 is what remained. At inference, where the task sets the length rather than a configuration file, the rest of the cost appears, and Byte-5 runs 3.7 to 6.4 times slower on summarization and 6.4 to 9.5 on classification. If shorter sequences are all we are buying, why stop at 200,000 entries and not 2 million? Because the cost rises at the other end of the axis. Every token the model produces runs a matrix multiplication against the whole vocabulary, costing twice the model width times the vocabulary size. So at Llama 3 8B's shape, 200,000 entries cost about 13% of the transformer body per token, and 2 million entries cost more than the body. Rows the model rarely sees barely get trained at all. Meanwhile, what we buy keeps shrinking, because quadrupling the vocabulary from 50,000 to 200,000 entries moved compression only from 3.85 bytes per token to 4.33. Two costs moving in opposite directions means there is a minimum, and that minimum has been measured. Tao and colleagues trained models from 33 million to 3 billion parameters to find it, and concluded that Llama 270B's vocabulary should have been at least 216,000 entries, where it used 32,000. The question asks why we do not move left along this axis. The measurement says we are already too far left. Byte-Level is not really the alternative to BPE, because BPE already contains all 256 bytes, so it already never produces an unknown token. The real variable is vocabulary size, and dropping it to 256 makes every sequence about 4 times longer. You pay for that 4 separate times in training compute, decode steps, the KV cache, and the context budget. At normal context lengths, that is a 4 to 5 times bill rather than the 16 times people usually quote, because most of the transformer scales linearly in positions, though the gap widens as the context grows. 4 sentences, and not one of them, names a technique. It works because it puts a cost on the trade-off before it gives an opinion, and because every number in it came from somewhere you can check. Our sentence stays at 12 tokens, not because some R and I's mean anything, but because 12 is smaller than 63. What if the split points were not frozen into a list in advance, but chosen while the text is being read? That does not move the marker along the axis, it removes the axis. The byte-latent transformer takes raw bytes and groups them into patches wherever the next byte is hard to predict, and its average patch is 4.5 bytes against Llama 3's 4.4 bytes per token, the same compression with no vocabulary anywhere. That tells us what the merges were giving us, which was not meaning and not a vocabulary, but shorter sequences. BPE is one way to get shorter sequences. It builds a fixed list of common pieces before training starts, but it is not the only way.